All right, and then out of those different types of stereoisomers, you have, we're going to discuss two types, enantiomers, diastereomers, right? And also under this topic of stereoisomerism, we're also going to talk about how to determine the number of stereoisomers, which we're going to do that actually right up front. And we're going to have to ID some chiral centers because that's really important in order to understand what an enantiomer is, or how you draw it, or how you determine what an enantiomer is. You need to be able to first identify chiral centers. All right, so let me bring up this picture right here. Right, this is Taxol. Right, it's a chemotherapeutic. It's harvested from the Pacific yew tree. Takes about 100 years for one of those trees to grow, and it's harvested from the bark of the tree. And even if you take the bark, you're only going to get a few milligrams. Right, so this had to actually be synthesized in a lab, and the novelty of the synthesis is the fact that you have multiple chiral centers in this molecule. So we're looking at, let me see. Hopefully, let me change highlighter so it's easier to see. So that's 1, 2, 3, 4. Not that. Sorry. 5, 6, 7, 8, 9, 10, 11 chiral centers, right? So Taxol has 11 chiral centers, and from those 11 chiral centers can all have different configurations. So the number of stereoisomers that you can possibly make is 2 to the 11. Somebody calculate that. Just put that in your calculator and tell me what you get.
I want to say it's 2048.
Say that again.
2048.
48. Okay, great. I agree. All right, so you have a possibility of 2048 stereoisomers, and that's a combination of enantiomers as well as diastereomers, right? 2048 stereoisomers. But in the body and in a cancer cell where Taxol is going to have to bind and somehow cause apoptosis, however it does it, only one of those stereoisomers is viable, right? So that makes the synthesis of a molecule like this and the development of techniques where you can set those stereocenters or those chiral centers, that makes that all the more important to be able to create a molecule like this or synthesize a molecule like this with specific stereochemistry, and not, so you want one out of the 2048 stereoisomers. And this is the one that actually works. All right, so you can see in this molecule, you can see that each one of these, let's just look at this little section right here. And you don't have to write all this down because that's a huge molecule. This will be posted. The notes of this part of the notes will be posted. So, but you can see right here with these 3 chiral centers here, here, and here, right? You can see that they are either going, they're all going on what we call a dashed line. And what that means is that they're going away from you back into the screen. And then over here on this chiral center right here, This is actually on a wedged line, right? And you can see that that is coming out. What that means is that that's coming out of the screen. So that's what we mean by stereochemistry. Is basically talking about the 3D orientation of a chiral molecule. So let's write that down. Let me add a page. All right, so when we talk about stereochemistry, when you hear that term, it's the 3D orientation of a chiral molecule, right? So when we look at this taxol, we can see that the stereo centers or chiral centers that are going back and the ones that are coming up, that 3D orientation, that's where the configuration comes from, right? So it's either going to be R or S, depending on whether how the groups are oriented around that stereo center. All right, so we're going to talk more about configuration later. We'll come back and talk about that here, but I want to introduce just a rudimentary example first. So let's talk first about what chirality. Somebody define chirality for me. If you watch the chirality video, tell me the first video. Tell me what the definition of something that's chiral is.
Is it it arises from a molecule no, it arises from a molecule containing a carbon or a chiral center that has, I think it said four, I think I'm saying this wrong, the riverent, I think, or the riverent, I think it's saying.
Substituents.
Yeah, so substituents.
So four different substituents.
It has a non, I think it's non-symmetrical,
Yep,
and,
non-symmetrical.
and it has the sp3 hybridized.
Okay, good.
And
Hold on, let me fix my little handwriting. I need y'all report me to the president. Non-symmetrical, sp3, hybridized, and what else?
it also says the mirror images of any molecule that is chiral will be non-superimposable.
Yes, that's the key. So the mirror images are non-superimposable. Excellent. So chirality is a property, and that property arises from the fact that an atom, most likely a carbon, but there can be other atoms that are not carbon that are chiral centers, like sulfur can be a chiral center, nitrogen can be a chiral center, but that atom has a specific set of qualities, right? It has four different things attached to it. It is non-symmetrical, which ties into the four different things attached. It's sp3 hybridized, which also ties into the four different things attached. And then the mirror images are non-superimposable. So those mirror images we call enantiomers. So the mirror image we call it an enantiomer. Right? By default, let me say this, even though we haven't defined configuration yet, by default, enantiomers have the opposite configuration because they're mirror images. Right? So every chiral center is going to have a specific configuration. It's either going to be, the groups are going to be prioritized and oriented either clockwise or counterclockwise, or R or S, right? So let me mention that. And then we're going to discuss how to determine that. So configuration is, let me fix that, the arrangement of the groups around the chiral center. right, around the chiral center, and that's going to be R, which is clockwise or rectus, and then S, which is sinister, or I'm just going to abbreviate that as counterclockwise. All right, so let's go back and talk about the enantiomers. So I built two molecules. Let me shift. I got to turn my video back on and make sure I'm visible. Where am I? I don't see myself. All right. So this is an example of this background is really screwing me up. Hold up. Let me turn it off. All right. So this is an example of what we would call a chiral center. All right. It has, so the central group, the black atom, the carbon right here, that's my chiral center. Or we can call it a stereo center. And you can see right away that it's sp3 hybridized. What does that mean? When we go back to and talk about hybridization, how can we tell if something is sp3 hybridized? What did we learn in part 1 that tells us that?
Isn't it like if I'm not mistaken, it's like whatever is attached, or how many like I want to say, is it atoms that's attached to the molecule?
Yes. So how many groups are attached to an atom that's sp3 hybridized?
Is it, I want to say it's no, I want to say it's no, it's 3, because sp2 has 2 attached to it, right? And then it's 3.
So
What, sp3?
okay, so sp3 is 4 groups,
4 groups.
Yeah.
right? sp2 is 3 groups because it's trigonal. An sp3 atom, that carbon in particular, is going to be tetrahedral, so it's got 4 groups attached. So you can see there are 4 groups. There's this white atom, the blue atom, hopefully you can see that, the purple atom, and the red atom. So those are my 4 groups. All right. And then it's non-symmetrical. That ties into having 4 different things attached. The moment you have 2 things that are the same, right, this becomes symmetrical because I can cut it right here and have the same thing on both sides. So the fact that I have 4 different things ties into the fact that it's non-symmetrical. And the hybridization ties all of that together, right? Because in order to be sp3 hybridized, you have to have 4 things attached anyway. All right. Any questions about that? Is that clear, that part?
Yes.
All right. So here's the kicker, right, about the non-superimposable mirror images. So that is a key to determining whether or not an atom is a chiral center, is if you build a mirror image or you draw the mirror image, you can't superimpose them. I'm not sure, I can't remember in the video or which video talked about superimposability, but all that really means is being able to lay the molecules on top of one another and line all the atoms up. All right. So if this is the image right here, right, is the lighting all right? Can y'all see the colors pretty good?
Yeah.
Yes.
So this is the mirror image. Can you see that? Hold up. Yeah. You see how the purple is coming at you on both images? So it's like looking at itself in the mirror. Can y'all see that?
Yes.
All right. And the silver atom right here is facing the other silver atom. The white atom is pointed up. Following? So if I wanted to superimpose these, what I would do is take one or the other and try to lay it on top of a second image and get everything to line up. So I want to show you now that if I try to lay these on top of each other, let me line up. So I'm going to turn this. I'm going to turn this one so that the silver atom here and here is pointed the same direction. So I'm going to turn it like that. Can y'all see that?
Yes.
Right? What's different?
They're red.
The red atom is now pointed where? Towards you, when before, when I had it like this, it was pointed away from you. Is that right?
Yeah.
Yes.
So now if I'm turning it so that everything is going the same direction, you can see immediately that the red atom and the purple atom are now in different locations in space. And if I try to lay these on top of each other, I can't get them to match up. The white is fine. The gray is fine. Y'all see that? But the purple and the red don't match. That's what it means to be non-superimposable. Are you following? Yes, no?
Yes.
The back, you turn it back, like you know how you had it matching, right? At the
Like
first
this?
time.
Mm-hmm.
Right. And so if you try to lay it over now, it'll go.
No,
but
it won't. How much you want to bet? Put some lunch money up.
I don't want to bet anything. That's what I was asking. I was
Just talking, just be talking and talking. No, I'm just joking. But if I try to lay it here,
Yeah.
everything matches except what? The red and the silver. You see that?
yes.
So there's a difference. And so this is an entirely different isomer. This one right here. So the mirror image is entirely different from the original image. So that's what it means to be non-superimposable. And we call the mirror image, which is this one, the enantiomer, right? That's the definition. An enantiomer is a non-superimposable mirror image of a chiral molecule. Is that clear?
Yeah. Because
right.
no matter where you turn it, it's still never going to.
Exactly. Because
Okay.
let's go back and define what a stereoisomer is. Because when we say that these are isomers, these particular types of isomers are called stereoisomers, right? Remember from part one when we learned about isomerism, it was, same molecular formula, different structure. A stereoisomer has the same molecular formula, it has the same structure, but it has a different 3D orientation. So let's write that down because that's going to help us as we move forward. Let me add another page. Right, so now we have a couple of definitions. We got an enantiomer, which is a non-superimposable mirror image, but we also know that an enantiomer by definition is what we call a stereoisomer, which has the same structure and the same formula. Same molecular formula. Come on, Albert. But a different 3D orientation. Right, what all that 3D orientation means is the configuration, how the groups are attached to that chiral center. Is that making sense? Are the models helping at all?
Yes.
All right, great. And again, if you can spare 20 bucks, they sell these kits in Auburn. You can order it online, but I'm not sure how long it'll take you to get it. But it's an invaluable tool, especially if you have a hard time visualizing things in 3D. Just build it and move it around in your hand. If you notice too, I'm not taking atoms and removing them. I'm just rotating in space. That's all I'm doing. Right? Are we okay so far?
Yes.
All right. So we know now about what an enantiomer is. We know what a stereoisomer is. We know that every enantiomer is going to have, let me say that too. If you notice how the groups are aligned, right? When I prioritize this structure, those groups are either going to be clockwise or counterclockwise. By clockwise, I mean when I prioritize these and I look here, here, and here, if I line them up in order, they're either going to be, I'm either going to be able to count 1, 2, 3 clockwise or 1, 2, 3 counterclockwise, depending on the priority. All right. And if whatever the configuration is of one enantiomer, the other enantiomer, the mirror image, has to be the opposite because it's a mirror image. We'll get to that in a second. I want to run here and I want to show you some. Let me cut this out because I'm gonna run out of space. I know it. I want to take this and we're gonna actually apply this right away. And I think that's the best way to do it. All right, so let me paste this here. All right, let's take that first molecule right here and look at what the instructions say. Draw the mirror image. That's all it's asking you to do, right? And if you'll notice here, there are multiple stereocenters. You got 2 stereocenters here. You got 3 here. We'll talk about all of that shortly. There's 1 here. And then there are 2 stereocenters here. All right, but let's take this one. All we worried about is the mirror image. And let's go ahead and do this too. Let's identify the chiral centers. Let's do that. So if we're looking at these, let me write this up here. And draw the mirror image. So if we're looking at those carbons that I have highlighted, how do I know that carbon, let me change the color. How do I know that carbon, the carbon that I have highlighted in pink, how do I know that that's a chiral center? What's the criteria for chirality?
There are 4 different substituents attached.
That's all I'm looking for. I know all the other stuff, but the first thing I gotta have is 4 different things on that center, right? So if you notice here, in this chiral center, I have a group here. I have a bromine here, I have a hydrogen here, and then I have another group down here, right? Because if you look at the bonds are like this. There's a bond to this group, a bond to this group, a bond here, and a bond here. So that's how I identify my chiral centers. I just look for an atom with 4 different substituents attached to it. Sometimes the stereochemistry will be defined, like in this example over here, where you have the dashes and the wedges. You know that those are stereocenters because they're defined as either going back into the page or coming out of the page. But right here, we don't have definition as far as like how that is oriented, whether it's back or up. We'll talk about that shortly, because this is an example of a Fischer projection. I think I need a C in there. All right, this is what we call a Fischer projection. All that is looking at, let me build this right quick and I'll show you what that really is. It's really literally looking at this molecule from underneath it. That's all it is, right? And so if you're looking at a carbon from the bottom, like so, right? That's all that means. So the horizontal groups are coming out at you, and then the vertical groups are going back into the page. That's why you can't see this purple atom, because if I look from below the carbon, then I won't be able to see that purple atom. All right, so that's all. So this is what we call a Fischer projection. So don't worry about, we're gonna talk about that too. But let's look at the bottom stereocenter. How do I know where are my 4 groups on that?
Would it be oxygen,
Iodine.
iodine,
Hydrogen, is that right?
the oxygen, and then the other carbon?
And then, yes, and then the carbon that's right here. And let me do that for this down here. All right, so those are my 4 groups. So both of those are chiral centers. Now the question is, what does the mirror image look like? There are a couple of ways to do this, but I'm gonna give you the easiest way for Fischer projections is to simply draw a mirror plane here and recreate the 2 stereocenters here, and then put the atoms back on, just like you see them. So if this was looking at itself in the mirror, what would it see? Right? It would see a bromine here. Is that right?
Yes.
Let me fix my old raggedy handwriting. You never took my class before. My handwriting is horrible, but I admit it. So hey, it is what it is. Would I see an iodine here? If it's looking at itself in the mirror?
Yes.
Yes. And then I see a hydrogen here and OH here. Is that right?
Yes.
And then an H here. And then the CO2, the carboxylic acid, will be here like that. Are we following? That's it.
Yes.
Yeah.
That's the mirror image. All right. And so when we talk about, we're going to talk about configuration, we're going to kind of walk this down. So we'll do the how to draw the mirror images first, and then we'll come back and talk about how to determine the configuration. Hopefully we'll get a chance to do that today. We might not, but it's okay. Right, so that's the mirror image for that particular molecule. What about if I had this molecule over here? Right, there's nothing, no rocket science involved about drawing the mirror image. I'm going to do this. I'm going to draw a mirror plane, and I'm going to draw exactly what I see. I'm going to recreate the chain. What is this, the mirror image, going to see first?
Chlorine.
Chlorine on a wedge. That's very important. If I change that wedge to a dash, when I flip it over and try to line those atoms up, that chlorine is no longer going to be on a dash. It's going to be, I'm going to show you in a second, but so when I draw the mirror image this way, I need to keep everything how it is. All right, are we following?
Yes.
All right, so what else, what comes after the chlorine?
The hydrogen and oxygen.
So the hydroxyl group, right? The alcohol. And it's still on a dash. I didn't change anything, right? And then I also have this still on a dash. I'm gonna draw it just like I see it, just like that. And those are my 3 stereocenters. So this is the mirror image. And if I draw it that way with the mirror plane, I have to leave all the stereocenters the same. And I'm gonna show you why. So we're going to leave those stereocenters just like we see them. All right. I can also draw that same molecule, but rather than drawing it with a mirror plane, I can just duplicate it, but change all the stereocenters. Right, and these 2 images are the same. All right, so depending on how I draw the mirror image, that'll determine what I do with the chiral centers that are present. I'm either going to leave them the same, which is what I have done here, or I can alter them. But notice how the molecule is drawn. You see how now everything is lined up? All the atoms are lined up. All right, yes, no, maybe, somewhat.
I said, so you changed everything in this one. I don't know if you can hear me.
Yeah, I can hear you. I can hear you just fine.
So you changed so can you just explain one more time what you just did?
Look at how I drew this one over here. What did I do? I drew a mirror plane, and then it's basically this molecule right here looking at itself in the mirror the same way you would if you were looking at yourself in the mirror, right? Your nose wouldn't be on the back of your head, would it? You'd be looking right at it. Is that right?
Right.
And so if you think about this first atom as the nose, when I draw this with a mirror plane, the first thing he's going to see is the nose on this side. You following?
Right. I get that part. I'm talking about the one at the bottom.
So this one down here is, let me just explain that part. So if I took the mirror image, which is right here, I have it labeled, and I flip it over like that, so I can lay it on top of the original. This is what it would look like, because everything should be different. Remember, if it's a mirror image, all of the configurations are the opposite. Is that right? Did we say that earlier?
Yeah.
Yeah.
So you flipped back over again. That's all you did.
Yeah, I just flipped it over to line all the atoms up.
Okay. Yeah. Okay.
Is anybody else not seeing that? That's why so this mirror image, I can take and flip it over. And when I do that, by default, because I'm not changing the atoms, I'm just rotating it in space. If something is on a dash or in the mirror image and I turn it over, it's gonna automatically become a wedge, right? Are y'all following? Yes. You see how like, let's just take for instance, let's go back to what we had earlier. It's not the same, but it's the same idea.
So Dr. Russell, I have
Go
a
ahead.
question. So the mirror image at the bottom, will
Mhm.
that be considered superimposable? Since
No, it's not superimposable, but it is drawn in a way that you could try to superimpose the mirror and the original. But if you can see right away, look at the stereo centers. This is on a dash, that's on a wedge. You can't lay those on top of each other. They're not gonna line up.
Okay,
Following? Same
Yeah.
thing here, that's on a wedge.
Yeah.
I'm sorry, a dash, and this is on a wedge. When you try to lay those on top of each other, they will not line up.
okay.
Yeah. So everything in the mirror image is the opposite of what it is in the original. What I'm showing you is just that there are two ways to draw the mirror image when you have more than one stereo center. How many stereo centers how many chiral centers are here?
3.
3.
Three.
How many stereoisomers do I have possible for that?
8.
8. Good. So I have 2 to the 3rd stereoisomers possible. Right? We're going to talk about what those other isomers are shortly. But right now I want to I'm kind of giving you some information, jumping the gun a little bit with information, but that's all right. We're going to get it. What about this one? The next one. How would you draw the mirror image of that? Oh, before we go to that, are there any questions about the second example? Whether, however we draw the mirror image, because we can draw it like we have it up top on the right with a mirror plane, or if we choose, we could just alter all the stereo centers and draw it like we have at the bottom left, the blue image.
It will always be right if we do the mirror plane, right? Like we
Mhm.
can always do the mirror plane. Okay.
Oh yeah. I'm just giving you more because see, once you have more than one stereo center, then you have more than one way to actually express the mirror image. You can express it like it is up top right or bottom left. And both are correct. All right. What about the next image? How would you draw the mirror image of that?
You will see oxygen first,
Good.
the double.
Like that. Is that right?
Yeah.
And it's going to be on a dash. I'm going to leave it. Is that right? And then what about here?
Oxygen and hydrogen.
So hydroxyl.
Oh,
and then
hydroxyl.
Here, that's okay. I got another hydroxyl group. These are not the same though, because there's a carbon between this hydroxyl. Right, there's a carbon right there. So they're not the hydroxyls are not the same. All right, and then over here I have what? A cyanide.
Carbon.
Is that right?
Yeah.
Mm-hmm. So this is the mirror image. This is what you call.
Well, are you forgetting? You don't have that. Does it matter if you don't have that dash in between the two?
Where right?
The carbon and the nitrogen.
Oh, you mean the triple bond?
Yeah.
I
Sorry.
can draw it either way. But
Okay.
since you said that, you're probably not the only person who's thinking that, so I'm gonna put it in. Yeah, that's a good question.
So the triple bond is insignificant. Like you can leave.
Yeah, it is, but it's understood if I draw the cyanide functional group as just CN, the triple bond is understood.
Okay.
Yeah, but I'm gonna leave it in there. All right. So I'm gonna leave this one for you to do. All right, so I want you to just follow the instructions, draw the mirror image, and then, well, first ID the chiral centers, and then draw the mirror image. All right. Any questions so far? We all right?
I have a question.
Go ahead.
Okay, so for the tetrahedral that we just did,
Mhm.
can we also draw it how you do it in the example before that, how you had two mirror images?
Oh, you mean, can you rotate it and?
Yeah.
Yeah, sure. You can draw it. You can draw the rotated image. What's going to happen? That's a great question, because see, these the tetrahedron is like the basic geometry for every chiral center, because it's sp3 hybridized. So what you could do is, if you wanted to draw it the other way, this is how I like to think about it, is like a rotisserie. You know, and I'll show you what I mean by that. You could put an axis through here and just rotate around that axis to try and line those atoms up, right? So when I do that, what's going to happen to the OH group when if I rotate it? Can you see make the arrow out up here? If I rotate it around this direction, right? And let me bring my video back up because I can show you that. So let's just say, for the sake of argument, that this is, let me see, the oxygen is on a wedge. So that's that. Let me take this off and put another atom on. Biscuit. All right. So let's say that the oxygen here is the red atom. Let's see. The aldehyde is going to be this green atom. You following? Cyanide is going to be purple, and then this group up here. Stick another. Even though that we only care about that for priority, right? I'm gonna do that. So this is oxygen. This is the aldehyde on the dash, and then so the oxygen is coming out at you. The aldehyde is coming back at me. That's the purple atom. And then the green atom is going to be cyanide, and then this is the OH group up top. All right. Now, if I built the mirror image of that, which I can and will, boom. And this will probably be the last thing we get to talk about, but it's cool. Boom. Green.
You went over priority though already, right?
I haven't. We just right now focusing on identifying the chiral centers and then drawing the mirror images. We'll probably hit priority in the next class period. All right. So this is, oh my gosh, you gotta be freaking kidding me. Sorry, the video just went out by itself. So this is the mirror image right here. Can y'all see that? See how everything is lined up, red and red, purple and purple, the alcohol up top, and then the green back here. Yeah. So I could also take this, the mirror image, and I can rotate it around. That's that axis that I drew through here. I can rotate around that axis to line those atoms up. Right? It's not going to change the configuration. It'll just change the orientation in space. So if I wanted to line these up so that the greens will overlap and everything else would be superimposable, even though it's not going to be superimposable, I can just turn this way like that. What do you notice? What changed?
Green.
The green is now pointed in the same direction. Let me see if I can hold these right. Right, the green is pointing in the same direction, but what about the red and the purple? You see the difference?
The red is facing you.
Right. When in the mirror image, when I had it drawn like that, it was like this, yes? Yeah. So anytime you have a tetrahedron and you want to, you can draw it like so, or you can just rotate around that axis to get it in a different conformation. So you can draw it either way. It's up to you. I think the mirror plane is easiest, but you could also draw it like this, where now this is change colors, and then this will be it. I'm gonna let y'all go after this. We will have the aldehyde will be, let's see, here. Cyanide will be here, and then the OH will be here. You can draw it that way. If you rotate again, you'll get the OH here. The aldehyde will be back here. The point is that you're not going to be able to overlap them. And the cyanide will be here. Right, so it just depends on like how you rotate around that axis. But
So,
go ahead.
so for the first mirror image, the oxygen it's wedged, so it's facing like towards you.
Yes.
And in the second one,
It'll be away from me because what I've tried to do is line the atoms up.
okay.
So I would basically turn that whole molecule over. So if I turned the whole thing and did not rotate around the axis, I would end up with this. So now this is the aldehyde, that's the OH, and that's the cyanide. Right? And if I tried to take this and lay it on top of this, I couldn't because the aldehyde and the alcohol groups wouldn't overlap. So that's how I would draw this, right? Because it's the same thing, I just rotated it around. But to me, the easiest way to do it is just to draw that mirror plane.
So you said for the orange one, you just rotated it?
Yeah, turned the whole thing over. So I just took the whole thing and just flipped it over.
Wait, do one more time?
I'm just, so if the red is the OH, and get that right, that's the wrong one. If the red is the OH and the purple is the aldehyde, all I'm doing is this in space. So I can lay it on top of the other one.
Okay.
Yeah. All right, we gotta stop. We are 6 minutes over, and hopefully everybody put your name in the chat. If you didn't, yes, I don't know if this question was earlier, but yes, I changed everything. All right, make sure your name is in the chat, and then we'll see you back here on Wednesday. We're gonna keep pushing. Wednesday, we're gonna start talking about configurations and RNS, and then we're gonna also talk about diastereomers and how to draw those as well. All right, any questions before we log out?
You said that our assignments are due before the.
Say that again.
You said that our assignments are due before the exam, correct?
Yes.
Okay, thank you.
Yep. All right, no
Yeah.
questions?
What
I
is
have a
the
question for after.
Well, I have another class at 10, so it's gonna be
Okay.
after.
Send you an email then.
You can just shoot me an email or a text, and I'll answer it that way.
Okay.
When is the exam?
2 weeks from Monday, not this coming Monday, but when do we start class? Friday?
Mhm.
Yeah, so it'll be 2 weeks from this past Friday.
Okay.
And it'll probably cover stereochemistry, and then we're gonna leave this topic and start talking about allylic bromination and synthesis of alkyl halides. So wherever we get to, that's what the exam will be over.
Okay.
Thank you.
All right, y'all have a good day.